Another draft physics video presentation. Yeah, I painted this like, I don't know, 15, 20 years ago, this gorilla. You can still see him. I'm beating the hell out of this shirt. It's amazing. Anyway, technology and such. Yeah, they can make things that stain for a very long time. But anyway, just surprises me. Anyway, Brian Greene. So this is just one of these. I'm just going to present. Okay, here's their argument, and it really is their argument. I mean, this is the similar story will be told by all of them. This is the narrative of their messiah of quantum woo, and it really is woo. It's an amazing, mysterious, wooey story about how this magical probability thing happens and the universe isn't deterministic and blah, 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 blah. And they don't, most of them don't come right out and say that. He actually does. And if you don't like it, tough. As Feynman would say, God does play dice with the universe. Really, these are earmarks. These are, whatever an earmark is, these are places you can focus on and say, well, it sounds like a religion, really. You're really saying there is a God, and you're really saying there is some sort of, a true action that is spontaneous, from whatever the magic source is. And it's just, so anyway, it's just for the purpose of that, and it all comes down to this two-slit experiment, and it all comes down to, some kind of argument that it's impossible to come up with some other explanation. We have to have this religious explanation because the world is too wacky and weird. And so I'd say it's not much different than the argument against Darwin's evolution, where people just keep talking about, well, how do you account for how many plants there are? Well, there's so much diversity and there's so much interesting things. And how could just a dumb forest create all that interesting stuff? And, it's just the same sort of narrative. And so, they have this pretense that they're above the bullshit, and they've, sat there and scientifically and clinically dissected this frog of life. And they haven't done any of it in any kind of straightforward manner. They're not as prone. Clearly, they don't fall for Jesus stories. But they're not much better, okay? They're not much improved on this scale of being clinical and careful and disciplined in doing this scientific investigation thing. They're pretty sloppy detectives. I accidentally dropped a gun. Ha ha ha. I accidentally placed some new fingerprints in the room. Accidentally. Come on. Alright. So all I can say is this is their story. This is the science, and I'll be insulted as some sort of anti-science, unreasonable, Dunning-Kruger, retarded, because I just don't sit there and say, oh yeah, that just so makes sense. That's so brilliant. Because it really isn't brilliant. When you look at their evidence, there's nothing brilliant about their conclusions.
About 100 years ago, a single generation of physicists.
So this was filmed in 2008, I believe, and I don't know how much of this we'll get through. I haven't even watched the Alan Alda part and the combo part. I know I've watched it in the past at some point, no doubt. But anyway, we'll just do this part, and then we'll see if the rest is worth doing anything else with.
Their work caused a radical upheaval in our understanding of the natural world, our understanding of reality.
Right, so it has to be our understanding, because only the reasonable and smart people, they all agree that this has to be our understanding, that space is bent and the small universe is all Heisenberg confused. We have to believe. You have no reasonable excuse not to jump on this little silly banjo bandwagon of bullshit.
And it's kind of surprising that, 100 years later, these insights have not been widely absorbed by the general public, but what if...
Well, widely absorbed, he means understood. That's right, yeah, they're still sitting there saying, what the fuck, that sounds so fucked up. I guess you know what you're talking about. You have some silly equation, right, that's really basically says, all the known things about the item, okay, including its probability, and then they just sit there and do Pythagorean, a 2,000-year-old formula to figure out. Oh yeah, we predicted it. I didn't predict anything. They put all the facts in and then got a fact out.
Is the case is that our culture has certainly adopted the language of quantum.
Yes, exactly. They have adopted the theme of woo. And what a big surprise. Human beings are decided to take the shortcut that aggrandizes existence and aggrandizes their functions. I have a quantum computer. We have now quantum biology, right? So it won't be long before they quantumize our brains. We're all randomized. Whoa!
Mechanics. Because, for instance, if we take a look at things like the quantum sleeper, every loving couple should have one of these. It gives protection from biochemical terrorist attacks, protection from natural disasters, from kidnappers, stalkers.
Right, so he's making a joke about how quantum mechanics has been distorted and perverted, and it's not a joke. That's really how people think of it, as a bunch of wooey magic. You might as well say anything, because your definition of what this quantum is so undefined. Your God has no features. You're just saying he's God.
It's a bulletproof, safe room, and you just have to sleep inside, sort of like Dracula. What I'd like to do here tonight, though, is just go a little bit further than the language of quantum physics and try to give you a sense of the logical progression of ideas.
Right. So, he's claiming there is a logical progression, that there was some sort of real clinical examination, and that they had even the resources at the time to do it 100 years ago, and that they were ready to draw conclusions. And they were a long way from ready. In my opinion, it's kind of obvious they were a long way from ready.
That led to this new picture of reality that you saw a little bit about in the previous video sequence, and then we'll take up some of the ideas that physicists are still struggling with today. So what I'd like to do toward that end is basically look at a sequence of experiments, each one of which is pretty simple to describe, pretty simple to explain.
Right. Now, the funny thing is, I'm saying, a sequence. You have more than one experiment? No. It's just the sequence of doing the double slit experiment. And again, it'll be in this order that he chooses to present the information in, with analogies that suit his purpose. It won't be showing you all the evidence and saying, this is the road we chose. Here's all these other roads, and we just said, nah, we're not going to bother with those roads because, this one has shinier rocks, so we're going with this road because the rocks are shiny.
But collectively, when we go through all of them, we'll come to a pretty startling conclusion. So the first...
You will, and your kind will, and your authorities will, and your poobahs will, and then all your little followers, all your little sycophants who, find it appealing to have, everybody has to be part of a gang and a club. And so you all become the little science nerd club or whatever it is. And you decide that, you're so much better than the dumb, ignorant religious people. No, you're not doing any better at all. Your performance is way below what the standard should be. Your arguments suck. Just like religious arguments, they suck. Your evidence sucks. And you have a bad theory because you have a bad process of developing theory.
Experiment has to do with a very simple idea that many of you no doubt have experienced. If you take a pebble and you throw it into water, you know that the water will kind of ripple outwards, right? Now we can create a version of that experiment.
Right, so we'll just sit there and say everything is water rippling. For what reason, I have no clue. I don't know why people think everything in the universe has to be rippling water. I don't know why that even makes sense to them, because when they think about it, when you really think about it, what's the water doing? Right? This water rippling thing isn't made out of some sort of magic. It's made out of some kind of process. So the pebble hits the water, what's it do? It imposes a bunch of acceleration, on a bunch of particles. It moves them, it hits them, it bangs them, it pushes them. And these little particles of water, they're real particles of water, molecules, they bang into each other in a certain way. This one doesn't bang into one way over here, right? That's not what happens. It has to transmit the movement locally. So this one hits this one, and this one hits this one in some cases, but some cases this one pushes on this neighbor and pushes him this way. And so the energy can move in different directions. Now, because this is sort of an aggressive, a bit of momentum, the odds are it's not going to do much of this deflection stuff. It's going to do a lot of get the hell out of the way stuff. And so you're going to end up with a bunch of water molecules that are basically banging into very specific water molecules. And you basically just have a bunch of radial force. This piece of force doesn't affect this piece. This piece doesn't affect this piece. No, it's basically just rays of energy going through the atoms. Okay, so we're back to an analogy where you understand that force has to be communicated between objects, and there's a higher probability that the communication will be in the direction of the force. It's not as likely for this to happen as it is for this to happen. Now, there are cases where this will happen on the subatomic level. We noticed that in electrodynamics, but the truth is, for atoms banging into atoms, the probability is going to be pretty straightforward. And there's no woo in here. There's no undeterminism in here. There's a bunch of atoms banging into atoms and pushing them one little step and just transferring the pressure, the movement. It just transfers it to another atom. And because they're a collection, you end up with a hump. This represents the fact that these as a hump are moving. So all of these move, and then the next, if you throw another, blah, blah, blah. See, the trick is when you throw the rock in, the water goes this way, and then it bangs into itself and goes this way again, and then it bangs into, it goes this way, and it goes in. So that's why you get more than one ripple. It's because as the rock penetrates, it creates a void, and then the water goes back into the void, and then it goes back out again. So, so you get more than one wave. But the single waves are just pressure. They're just movement, a little nudge. And the nudge means you have more atoms in the same space. If I put more atoms in the same space, I end up bulging the water because water's not compressible. So the atoms can't get any closer to each other. Molecularly, they can't get closer to each other and stay that way. So they force there to be a bulge in the water. So even if you want to live in this I'm a rock falling in the puddle of the universe bullshit, you still have to understand there's a physics to it. It's not a magical analogy that just stops there, that there's no dissection of the analogy. You can dissect the analogy and find the real mechanism, which is radial pressure.
Same idea, where we have water that's heading toward a barrier that has a slit in it, and through that slit the water progresses, and you have a radial outward pouring of the water. And on the screen,
Right, so they're deliberately representing that everything is the same thing, and it's not. So obviously water does a specific thing, and it creates these bumps for the same friction kind of reasons, that water molecules stick to each other. So if you slow some of them down by having a surface in the way, well, you're going to end up bowing the wave because some of the water is moving slower than the other water. And it's going to be bent by that process. Not magic.
putting it very bright where the water is agitated quite vigorously, and then the screen goes darker and darker, you can see from the far left and the far right, because the amount of agitation gets smaller and smaller as you get further and further away from the source of the water.
Right, so because of the way he's drawing it, they're making it look like, oh, look, there's humps there, there's bumps. But those are moving ones. They're not standing waves in one place, so that wouldn't be an interference pattern. Okay, but that's not what the single slit does in light anyway. It does the same thing that, the light in the double slit does, and it creates bars and locations.
Namely, the single slit. So pretty simple idea, just waves in water. The second experiment is a simple variation on this one, where I'm going to put a second slit in the barrier. And as you can picture in your mind's eye, and I'll show you in a moment, now what will happen is you'll have these radial waves emanating from two places. And the wonderful thing about waves, the real distinguishing feature of waves is when they cross, something really interesting happens.
So again, when they cross, like they're just something we don't understand already. We know it's pressure. We know it's atoms under pressure. And obviously, if you can't compress the stuff and you mix two things that have stuff in them and you mix them, they have to add. So that makes sense. And we know the other part of the wave is low pressure. It's an absence of water. So if you add where there's an absence of water, and you take where there's too much water, where gravity's basically saying these two are uneven, and you crash those into each other, you're going to equalize the pressure, and you'll go back to normal again. So that's not interesting. I mean, hardly surprising.
As you can picture, if the peak of one wave meets the peak of another wave, the water goes higher. If the trough of one wave meets the trough of another, the water goes lower. But the key thing is, if the peak of...
All right, well, so that's the tricky one, right? The trough meaning the trough goes lower? No, it's the trough.
of one meets the trough of another, they cancel each other out. Waves can cancel each other out, so there are places where when the two waves cross, the water won't be agitated at all. So let's just take a quick look at that. Here you have the two slits. The water goes through. You have the waves emanating from each, and it's overlapping. And
So now they're showing the slit pattern, blah, 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 blah. And again, this isn't applicable in a lot of ways. This isn't the same pattern. It's not even the same event, right? We know the water's going up and down where they're showing that bright line. That means there's agitation there. That means it goes from completely on to completely off to completely on to completely off, right? Where in the other spot just stays the same all the time. So even the way he's showing it, he's showing us what light does. He's not showing us what the waves actually do, which is on, off, on, off, on, off. Right where that light bar is, it goes from double bright to double dark, by their theory, and where double dark, and where the dark is, there's really a neutral, a zero, you know. So it's going positive, negative, where the bright bar is, and it's going nothing at the dark bar. But again, he's not showing that because, you know, that wouldn't be analogous. The analogies would start to break down if they used the real images.
on the screen in the back here, I now have placed a very bright band where a peak and a peak meet, or a trough and a trough. But you can see that there are dark bands. That's where a peak of one wave meets a trough of another, so there isn't much agitation of the water there at all. And this...
So, I mean, this simulation's kind of dopey because it's not even correct, right? I mean, they've got the bar pattern doesn't match the little spiral pattern the waves created. You know, so they can't even be bothered to have anything that looks that's correct, right? I mean, these lines should be going right to a bar. There shouldn't be a bar in between them and in two darks. I mean, you know, this is when they're trying to be, you know, professional propagandists, and they can't even do it with any consistency.
image that you have right here, this alternating sequence of bright, dark, this...
All right, turn the volume up a little. I mean, I thought it was louder than this. I don't, you know, sorry, in the middle of a video, changing the audio settings is probably not a great idea, but he seemed louder before. How come I can't get rid of that now? Oh, God, I hate this little window is nice, but yeah, it's really stupid if you can't get rid of anything. Ugh, you have to do this horse shot every time.
This is the telltale signature that you are dealing with waves. This is the real feature of waves, that they can interfere, cancel each other out, yielding those dark...
So it's only one kind of wave, right? I mean, it's a wave that you're saying is in a medium of the surface that this phenomenon happens on mostly. You know, it goes down, but it goes up easier than it goes down. That's why it doesn't go down, because down means it has to push other water out of the way and has to fight against gravity. So the wave goes up because that's the less pressure. Up. There's more pressure down, so the wave ends up going up. So it's a very specific kind of medium. It's a flat medium, tension, water molecules, and a certain, you know, that obey certain rules. It really isn't something you apply to everything in the universe. And just call it waves. The magical wave. I mean, obviously waves and other mechanical devices will be working because of completely different dynamics.
bands in between the bright bands. It's as if you had a row of little boats back there, and each of them is equipped with a light, and they're going to turn on the intensity of light to match how much they're being agitated by the water. Where it's very bright, they're being agitated a lot. Where it's dark, they're not being agitated at all, because that's where the waves are canceling each other out. So this is the one thing that I'd like you to keep in mind. If ever we see in the next few minutes this kind of pattern, light.
Canceling, see, it says canceling each other out. And what happened to the double trough? Where did that go? Wasn't that supposed to be somewhere in here too? See, they're saying there's a cancel part, okay, where the big wave hits the little wave. But where's the part where two negative waves hit? Well, anyway, it doesn't matter.
Dark, light, dark. You should immediately think waves. I mean, I would love it if, you really took that fully in so that, if someone were to wake you up at 3 o'clock in the morning and say,
Right, so we're basically, this is brilliant science, is to say every time you see the simplest pattern the universe can create, which is an on-off pattern, it's the simplest piece of code you can send. Dot, dash, dot, dash, dot, dash. Simplest piece of code you could possibly make. And he's saying every time I see it, I should see one thing. Oh, it's waves interfering. Nothing else could cause that pattern. It's the simplest pattern in the universe. Why would I think anything else could possibly make that pattern? That's it. He's saying it. Come on.
have dark, bright, you say that's waves. And then you should send that person, for some help or something like that. But this is the key message. That is the telltale signature of waves. Now I'm going to go through.
It really is the telltale signature of a million other things, too.
A few other quite simple experiments that at first sight.
See, they've waved everything, right? So now, yes, two binary stars do on, off, on, off, on, off. They do a pattern. Now they're waving, because they have.
Won't seem to have a direct relationship to what we just spoke about here, but then we'll bring it all back together in just a moment. So this next version is we're going to replace the water by little bullets, little pellets, particles, not waves, particles. Let's take a look at that. So this device over here is just going to fire some bullets, and as you can see, sometimes the bullets.
So again, the experiment really is, the two-slit experiment has all of its reality in the sense of it being a light phenomenon. So they show to always talk about photons first and then go changing the mediums, changing the mechanisms. Because again, this built-in assumption is this is all the same thing. It doesn't matter whether I'm shooting photons or electrons or baseballs, that somehow this phenomenon is all the same for all these different medias. And again, this is not good science. Why should that be your assumption?
Make it through, sometimes they don't, but the key thing to look at is when they do get through, they hit the detector screen in alignment with the position of the slits. What could be more simple? If they get through, they propagate, they travel all the way to the screen in alignment with the particular hole in the barrier through which they passed.
Right, so again, this is just basic stuff, but again, they've gotten these slits way far apart from each other, again, as if the gun wasn't firing parallel, coherent light at the two slits, that the balls were somehow coming through at angles, and therefore they spread more with distance, when they wouldn't be doing that in the experiments. The experiments would always have the beam much bigger than the slits, and therefore the beam shooter is much larger than the slits, therefore there won't be any angular perspective here. So again, it's just a wrong perspective. It isn't an accurate description, blah 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 blah. Now we know if I shot, if I had a slit this wide and I shot tennis balls through it, we know that some of them will deflect. If I had to just make the slits not deep, make them thin, we know some will deflect, and you'll go in all kinds of places. And if I make the slit just barely like two tennis balls wide, we know we're going to get a lot of that's going to happen, right? The majority, actually, of tennis balls will hit one of the two surfaces, 50-50 at least. So 50% of light is going to be in some way deflected. I mean, there's lots of avenues of reasonable thought, and they just closed all the roads. Now, we're going to our Messiah of Sillyverse.
So this is what you would expect to happen if you actually did this experiment, and this is in fact what would happen. But here is the thing.
So again, that an animation was crap. It isn't what would happen. The theory would be is if the two slits are a millimeter across, then it doesn't matter how far I go 10 feet away, they're still a millimeter across.
I now want to do a version of this experiment with one change. I'm going to make the bullets small, really small. I'm going to make them perhaps...
So this is another kind of almost a, I shouldn't have to even explain this to, but they're going to imply that photons are really small. And yeah, the elements in photons we know are really small. So if they did some real, like one of those evolution pictures with the monkey turning into a man, well, if they did some real drawings to get real scale, I mean, if I said this was the size of an atom, and then you have this problem like, oh, well, the electron's, really, really small. It's smaller than that dot in reality. And the photon, the element of a quanta anyway, the big magical quanta, is clearly much smaller than that electron. It's like the same kind of proportion, much, much smaller. But what we do know is that this quanta, when you make it into a photon, okay, when it's a photon, that quanta ends up getting really big in its polarization. It's pp. It's really big. It has a big pp. And so the truth would be is that the polarization of the light, that is, we know the photon as it's in a container, okay? Maybe the quanta is really small, but the container called photon is huge. I mean, compared to an atom, okay? Now the photon is huge even compared to an atom. Okay, I mean, I drew that even wrong. The atom's this big compared to the photon now. So we know that the composite, that is the photon, has a quality that makes it bigger, okay? It makes it the big thing in the experiment. It's huge. So this is part of the, like what, you have to be a nuclear physicist to figure this out? Huh? They know what polarization is. It's not a magical thing they haven't known about for a long time. Why are they saying something that just isn't true? So in the light experiment, the bullets aren't really small in the sense that the thing called a photon certainly isn't small. And it's going to get screwed up by even a very, even a pretty big slit is still going to screw up a lot of photon. But that's the facts. You don't want to deal with those. Let's not talk about the actual circumstance. Let's just keep doing the fabiology. And let's ridicule anybody who points out those aren't the facts. Yes, let's beat the fuck out of them. Let's make them obscure. Let's downrate their credibility. Let's insult them, because that's just wrong. To make a counter argument that's connected to actual facts? No, we can't have that. We're physicists. We're scientists. We don't do that. Facts? No. We do fables.
Perhaps a billion times smaller than a typical bullet. And I'm going to use as these little bullets little tiny electrons.
So the electron experiment is dangerous. And so this is something that it has occurred to me recently that these experiments are really flawed. Photons are not electrons. So they're not the same thing. One is a little charged body. It's kind of interesting how you fire one is completely different. It doesn't have any polarization. There's lots of rule changes for the electron. So you move one of these little negative things by creating a mechanism where it's on a surface. You heat the surface. It's in the drawing, right? So you make it very energetic, and you basically spew energy, the electrons, off the surface by putting a positive over here. So they're ready to leave because this is hot, and you've broken the atoms. Essentially, you're breaking the atoms. Now let's understand, heat does create something called light, all right? And what it does create is a lot of radiation. We know that it's creating a lot of infrared rays. Different kinds of rays are coming off of this heated metal. So there isn't just, okay, the electrons that are going to be shooting towards this positive I've set up over here. I've made a little bullseye positive for them to come towards. And I put a little hole in the bullseye so the electrons accidentally go right through the hole. They go right through the target. So that's how they have to shoot electrons. And then the target gets complicated because obviously electrons again are charged, and whatever you put over here is going to end up being not, it can't be charge neutral. It's not possible to make something that's truly charge neutral because it's matter, and matter has protons, and it's going to, and it has electrons, and it's depending on where the electron goes through here, it's going to be screwed up. It doesn't, who knows where it's going to go. So the whole theory of shooting electrons is a little bit silly. And the key factor is this light, this other radiation that you're shooting. When you're shooting the electrons, you're shooting a bunch of other radiation with the electrons. So even if you have electrons, you got a bunch of this wavy crap that they talk, these photons are going with it. This stuff that you're shooting isn't just electrons. That's not the only thing in the beam of you're shooting. And so when they do the experiment with electrons, sort of the fakery of it is they use like a phosphorescent material, and this stuff actually does light up when you hit it with an X-ray. Okay, so an X-ray will light up this stuff, and there's every probability that with your electrons you're shooting a bunch of X-rays are going with it. Low energy ones, high energy, who knows how many of each. And so then when you're taking a photograph of what you're lighting up, maybe you're just doing the light experiment again, And so you have to see what these how far this pattern is. So I haven't done the math for it yet. Maybe somebody can find the math for the actual experiment with electrons. Because, this will tell you, right? This distance, okay, on the wall, on your receiver, and then as long as you know the distance you are from the emitter and the slits, you know this distance, okay, and you know this distance of the pattern, you can go back and find out what the wavelength is of the source material, and would be interesting to see if the wavelength turns out to be within the X-ray range. And that what all they've really done is do the light experiment. They're just detecting the X-rays. Who knows? I'd say it's an open question. So there's no good theory for electrons creating the pattern, because they are the bullets. And there's, they're not a composite object. They're not something you can say you damaged it and you refixed it, or you put it back in phase, or any of that crap. Because they don't have waves, they don't have a wavelength, they don't have any of that crap. There's no mechanical way to build it. So there'd be no reason for them to scatter to different locations based on anything other than physical interaction with other electrons.
Tiny bits of matter. So it's the same experiment. I'm just going to fire it with these little electrons. And what would happen there? Well, this is what you would expect to happen. Right? At first sight, you wouldn't think that by simply making the bullet smaller, you get anything different happening. So these little...
Alright, so again, you would expect, though, that yes, no matter how small you make them, some of them, depending on how small the slits are going to actually hit the slits. Deflect. And if I made those slits, right, this is all just thought experiments, so, we can all figure this out. That all I have to do to his animation to make their whole theory go away is just say, well, on the surface of the slits, when we have this slit, what I'm going to do? I'm going to put little flapper thingies, okay, little things that stick out and could be, little pieces that they can be hit, and they slow the electron down. They change its momentum by, they're like on little hinges and they can spin. And so I'm going to put these little spinners right here on the surface, or these little flippers. And then you'd understand that, oh, well, if I do that, then when I shoot the bullets through, some of them are going to get changed in their momentum, because they're going to get hit that thing, and they're going to deflect this way, or deflect that way, or deflect that way, and they're going to scatter off those two surfaces. So all I have to do is put something on the surface, some sort of arrangement of extra surface, and that's going to cause a transfer of energy. So all I have to do is steal a little bit of the electron's energy on the surface, and I've already explained why they're going in different directions. But again, the switching from water to photons to electrons, as if we are quite certain it's all the same thing. The magical same thing theory. Everything's the same thing. It looks like it is like. So a platypus really is a duck, just pretending not to be one.
Little tiny electrons are fired through the slits, and this is what you would think would happen. But when you actually do the experiment, it's not what happens. When you do the experiment, that's what happens.
So, and again, so he shows us a pattern, right? But we don't see the whole picture. You know, they should show us the fringes to see if they're there. Are the extra, is the envelope pattern there in electrons? Now, I've seen images where it is, and I would argue that no, if you've got the fringe pattern, then there's no way those are electrons. You're just pushing other crap through the experiment. There's more than electrons traveling, and you're detecting the other stuff that also lights up your detector. I mean, there really isn't a great way to detect the difference between the right energy of electron hitting something and the right energy of a photon hitting something. The two events carry the same amount of impact. So there's no rule that says I can tell the difference between when an electron hit or when an X-ray hit.
You get waves. That is perplexing at first sight, because where are the waves? We just have little particles. But then cooler heads can prevail and say, you know what? Take a deep breath.
Cooler heads? Yeah, sillier ones. That's all. So you're just using the word cool for something that's not cool. Okay, that's lame. Lame-brained even.
If you have water waves are composed of little H2O molecules. So maybe what's happening is similar to what happens in water waves. The H2O molecules bang into each other as they're passing from the source to the screen. Maybe these little electrons are just banging into each other on their way, and that's how they're creating this interesting pattern. So what do you do to see if that...
I guess what he's trying to imply is the more complex argument, which would be electrons are charged, which means they hate each other. So as they move through space, if you try to contain them, they will spread automatically just because they hate each other. So the beam spreads more than other beams would spread because the elements of the beams, the bullets, don't like each other.
That's the case. Change the experiment a little bit. Rather than fire this huge torrent of electrons all at once, fire them one by one.
Right, and even this is kind of a, like it's so easy to do. We have the single electron shooter. Yes, you can slow down how many electrons hit a target. But again, are you sure they're electrons?
One by one. So let's do that. One by single one, fire these guys, and each one lands at some particular place on the screen. And if you sit back and you wait, dot by single dot on the screen, you in fact build up that same pattern, that interference pattern, which is the telltale sign of waves.
So again, there's just no conversation about the real telltale pattern, which is the one that has two patterns superimposed on each other. So he's leaving out a huge element of the magic of the two slit, and for the sake of what? Yes, to make this, to create an ability to make up this silly story, to make it a fable.
We're learning that somehow individual particles themselves have a wave-like character. Now, you could say to me, that's...
A wave-like character in what? How so? I mean, I don't even understand why you people... I just can't even understand. I just can't. It just doesn't even make any sense. What's a wave-like character? What the hell does that even mean?
Just animation. I could do that. So let me show you the real thing. This is an experiment done, about 10 years ago.
So somewhere around 1998.
Which was the first time to really execute this particular thought experiment that physicists had written about and used as a pedagogical device for many decades. These are some scientists at Hitachi, firing electrons at a screen through the two slits, one by one, and watching them build up a particular collection of data points on the detector screen. Now, you have to wait a long time for you...
Yeah, so I would like to, frankly, like I said, they should be able to tell you what the wavelength of the electrons were based on the distances, and all that math should work. So if their wavelength turns out to be the same as an X-ray, well, then maybe this isn't what they think it is.
to have enough points to really see what's going on. So luckily for us, we speed this up a little bit, and you can begin to see a little bit of that telltale sign of waves emerging, but it's still not quite clear. It's starting to come a little bit more into view here. You can begin to see it, I hope, the bright, the dark, the bright, the dark. And as it begins to fill in with yet more of these electrons, the interference pattern becomes...
So, and again, we have another view that doesn't seem complete, right? Where's the rest of it? Why don't they show us what's over here and over here? Because that's where the second pattern would be if it's there. So we don't know. Was it there? Wasn't it there? Was it a real two-slit pattern like in light, or was it not? This is manufactured. I'm just saying there is an answer. They know the answer. We don't get to know the answer. But there is an answer there. And apparently they didn't like that answer being shown, so they don't show it. Clearly. So why would electrons create a different pattern than photons if it's the same phenomenon? Why is there no envelope, right? But like I said, I've seen the electron, so what's claimed to be an electron experiment that has the two patterns. But again, the argument is their way of detecting electrons was cheap and easy, which is they just used a phosphorescent screen, which is going to be excited by X-rays. And unfortunately, electron guns are also X-ray guns.
Manifest. So what is this telling us? This is telling us that little individual particles somehow have a wave-like character. It's telling us that we really have to think of the electron.
A wave-like character, a wave, just, no, we don't have to think that at all. It's an on-off pattern. All we have to think about is, well, why do they go here and they don't go here? Or why do we see them here and we don't see them there? Which might be the more important question. And again, how deep have the tests gone? Again, a simple thing I've brought up that might illustrate something. I mean, it gets tricky in terms of figuring out what kind of target you hit, because it can't be reflective to just one thing and then absorptive to another. But the argument would be is you could just take the double slit pattern in light and you could look at it with an infrared camera and see if there's any difference in the heat pattern, because technically you would argue there must be, because some of the photons are being absorbed. They don't all reflect off the surface. So especially if you make the target absorptive, is there a difference in the heat coming from the two different locations?
As it's traveling from the gun to the screen, kind of like a wave. So the picture, roughly, that begins to come into focus is as the electron traveling, you should think about it as somehow some kind of wave. And the wave passes through the slit.
Yeah, somehow some kind of wave, which again, just what is that? Sorry, it makes no sense. I should think about a dog as some kind of wave. Why? Why would it do that?
And the waves overlap just like the water waves, and when they get to the detector screen, they yield that interference pattern.
All right, but it's not the double slit pattern. So again, does it make any sense? She's showing double slits, no double slit pattern. So it's hardly accurate.
Now the thing is, this raises a lot of thorny questions. And physicists from 1920 or so through the 30s really struggled with this valiantly.
Okay, so he says that these physicists struggled with it valiantly. They're all etherists, okay, essentially. I mean, Einstein, you could argue that there was some point where he's arguing for a particle mechanical theory of photons, but then his bent space theory is clearly an ether theory. So, I don't know, that's so schizophrenic. I mean, Einstein's it's very schizophrenic. What Einstein did, because one of his theories is completely dependent on bent space, a non-mechanism, and the other argument is no, it's clockwork, it's all push, it's just little things banging around. For quantum mechanics, it just doesn't make any sense. But the rest of them are all just wave nutters.
The people that I have in mind are people like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Robin Williams. That's Schrodinger up there. Doesn't look like Robin Williams. So these guys struggled with this for a long time, trying to figure out, if the electron is a wave of what? What is doing the waving? It's hard to see what that could possibly be. And it wasn't any of these gentlemen that figured it out. It was a graduate student named
So he figured that out. He figured it out. It's just complete nonsense. He didn't figure anything out. He just decided to woo everything, even though it's not wooable. Even though there's no evidence of the woo, he just said, yeah, everything's wooed.
Louis de Broglie, who in his PhD thesis came up with the answer, and was an answer for which he would receive the Nobel Prize. It was the first time in history that a PhD thesis led and was awarded the Nobel Prize.
Right, because everybody deciding was all wavy people. They're all wavicists. They're all etherists. So yes, they went for this bullshit. Let's turn everything into a wave. So an electron now has a frequency. Even though there's no way to generate a frequency, even there's no mechanism giving it a frequency, we're just going to say that it's a frequency. We're going to turn the word frequency into the word momentum and pretend we don't need two different words anymore. I mean, that's it. That doesn't sound like a brilliant idea to me. You have separate words. They make sense. Momentum, frequency. But I know those are two fundamentally different things. One is mass and velocity. The other one is periodicity. One's a time thing. And well, anyway, just
Prize. And his idea was this. He said, if I'm watching these little individual electrons travel from the gun to the screen, and I'm finding them landing in all sorts of different positions, which fills out this pattern that I know must be associated with a wave.
All right, I know it must be associated with a wave. On-off pattern must be associated with a wave. No other way to generate such a pattern. Again, that's not good logic.
He had this imaginative leap that the wave was a wave of probability. A wave of probability. And what he meant by that was when the electron is in transit, all you can really say about it is the probability or the likelihood that it's here or here or here. And when the wave is big, that means there's a high probability that the particle is there. When the wave is small, there's a low probability.
Yes, so first he gave them a frequency, which is really what he did, okay? And obviously this frequency gets turned into, okay, some kind of wave probability. But that's the right order of events.
That it would be there. And that means if you fire a lot of these electrons over and over again, the way in which they'll land on the screen is dictated by that probability profile. Where the overlapping waves are big, you'll get many electrons. Where the overlapping waves are small, you'll get very few electrons. So if you go back...
So, as properly dissected again, this just has to do with distance of point sources where the light is scattering. So scatter explains the two-slit. I've already explained it, so I won't explain it again, but yeah, it works. And you don't need any of this woo.
To this little picture, here is the wave of probability. It overlaps with itself, having places where the wave is big or small. And where the wave is big, a lot of electrons will land there, because there's a high probability that they will. But where the waves cancel out, very few or no electrons will land, giving rise to the telltale pattern, bright, dark of waves.
So again, it's a fake notion that the electron has any probability other than the fact of a physical interaction it's going to have with the physical universe. There's no probability without rolling the dice and bouncing them off walls and doing all that stuff. If you're not going to do any of that stuff, the dice just don't flip on their own. So it's all just a nonsense.
That's the most astounding moment, at least to my mind, in the history of our species.
Amazing statement. It looks like it must be the same as, that's all. Sure. Looks like is like.
Thought from the time of Newton that the universe was very much like a clock, right? That was the metaphor that Newton liked to use. The universe is just sort of wound up, you let it go, and it evolves. And you can predict with absolute certainty how it will look at any given moment if you know how it is at previous moments. But this tells us that...
And again, the dice is a physical event. I roll the dice, there's physical processes that take place that turn the dice that will decide what the dice will look like. They're saying that isn't true. Those dice are really randomized by God. God decides what the dice say. The God of the universe, the God of the spontaneum, okay? Spontaneum decides for the dice. It's never a physical reality. There's not a physical interaction. The dice are waving in some unknowable way, and those waves are interacting with all the unknowable waves of all the other entangled wave particles. I mean, so they're really saying that, there is nothing reliable in any event.
That's not how the world works. Even if you know how things are precisely, or as precisely as possible, there's an element of probability that comes into the story. There's only a likelihood of things turning out one way or another. And the discussion that we will have in just a few minutes, we're going to probe this idea, try to tease it apart, and really see what it's telling us about the nature of reality. But there's one question I'd like to quickly address first, which is the most natural question to ask. If the world is fundamentally probabilistic, if all you can say is the electron might be here or here or here, and if the laws tell you the probabilities of it being at those locations, but that's the best you can do.
So let's understand the mechanisms that can create these probabilities are pretty simple, right? I mean, this isn't all that hard to figure out. So I would argue for one specific thing is causing most of this electron erradicacy. So obviously electrons are attached to protons in atoms, and the electron can be in different positions when a force hits it, and because of those different positions, of tension, if I hit the electron when it's in this position, it'll get a different deflection, this way, the deflection this way against this electron, so you'll get different vectors of response out of the electron depending on what position it's in relative to a proton when you hit it with a force. So that's what I would say is accounting for scatter. It can go in any one of these directions based on the tension of the electron. But you could also just understand it as I could just take the two things banging into each other. All right, and I could just say if I hit this with this, sometimes I hit it right in the center and it bounces straight back. Sometimes I hit it over here and it angles down this way. And sometimes I hit here and it angles that way. So I can explain scatter in lots of ways. I can explain why there's a certain likelihood of a certain event. And these would all have probabilities. The probabilities of this event, the perfect reflection, would be the same as the probability of the almost perfect deflection, barely a deflection, and this kind of thing. So I could figure out what the probabilities are, and but there'd be nothing magic about them. None of that crap is necessary.
Where does the definite world that we know about come from? Right? I mean, you all probably think I'm here. I think it too. So where does this definite reality come from? And I'd like to just begin to address that question. We'll talk about it more in the panel. But to address it, what I'd like to do is just compare what the probability wave associated with a small particle like an electron, how that compares with the probability associated with something large, like me or a baseball. So to do that, I'm going to imagine that I have an electron, and I put it here, say on a table if you will, and I let it go. Now just before
All right, because they've made an equivalency between frequency, that is how fast your wave is vibrating, and mass, because of momentum. So they've decided momentum is equal to frequency, how fast you're vibrating. So by doing that, by making that equivalency, they're saying the more massive you are, the higher your frequency. So obviously our frequency is so fast, that it's imperceptible. The amount of change in us is not detectable because we're oscillating. So there's so many frames per second that I can't even freeze a frame because there's too many frames in a second, almost kind of thing. It's like it's too perfect a vibration that I can never isolate the vibration, almost kind of thing. So yes, I could never know what I was doing at any one time because the moments of time are so small that I can never detect what you actually are doing at any one moment. Kind of a nonsense like that. So we don't look like we're waving because we're waving so fast. That's sort of the argument. And it's silly. I don't know, some more, we'll just
let it go. I know where the electron is with absolute certainty. It's right here, which means the probability wave must be really big over here and really small everywhere else. And I'm going to show you a picture of that, just a little cartoon of it in a moment. You'll see a very spike-looking shape, and that is indicating the position of the electron. So let's take a quick look at that, and then I'll let the electron go and watch what happens to the probabilities. So if I...
All right, so let's understand. Electrons don't fly very straight. So yes, this is true for electrons. There's some sort of unknown because they're charged, and you'd have to have exactly the same amount of charge in their environment that they're traveling through for them to behave the same way. And the odds of the universe stopping all of its moving and changing so the electron can duplicate the same experiment, that's pretty thin. It's pretty unlikely that the experiment you're actually going to do is going to be the same experiment with two different electrons at two different points in time, because the whole universe has changed. There's a bunch of force flying through, and there's all kinds of effects, and those effects are going to be subtly different for each experiment. So you're not going to be able to have a controlled environment to pass an electron through to say, yes, the electron always does the same thing under the same circumstances. You can never create the same circumstances.
Give that a whirl. There's some probability that these devices don't work. I did the calculation earlier and thought I was in good shape, but let's give it a, there we go. So the probability started spiked, but then it spreads out. Right now, the electron could be at any of these locations with the size of the wave telling us the likelihood that it's there, but then if we look and we measure the electron, we always find it.
So this look thing is just so insane. They're saying looking is every time a piece of radiation hits you. You know, a photon from the cosmos comes flying at me from billions of light years away. Right now it's hitting me, right? There's starlight, even though I can't see it. There's starlight photons hitting me, right? And every time that happens, oh, I've collapsed the wave function. I measured something. I didn't really measure anything, did I? No. But that's a measurement. And then somehow I get unmeasured again, and I go back to being a wavy nutball. So every time something hits me, I stop being a wavy kook, and then all of a sudden, I'm right back to it again the very next moment. I'm right back to being all confused about where the fuck I am.
One place or another. We never find sort of a third of an electron here or half of it there. When we do the measurement, somehow, in a way that we'll discuss later, the probability, the fuzzy probabilistic haze collapses to a definite reality. Every time you look, the electron says, I'm being looked at.
All right, so, I mean, this is good science? No. Nobody will say anything like, oh, yeah, that's shit science. It's garbage. It's propaganda. It's bullshit. It's a storytelling that's not even accurate. It's just terrible. But none of you will say it. Okay, because it's one of your people, one of your little sillytons, you know, and so, you can't admit that this is way beyond what the evidence indicates. You can draw conclusions and say for certain, way, way, way beyond reasonable, scientific. This isn't an intelligent conversation. He's not inciting intelligent methods of thinking. All right, so enough demonstrated. Really, it's just too pitiful and sad and horrible. With all the, just, it's like I said. I have through my whole life, I have colossally overestimated the underlying capacity of human beings to be at all reasonable. I thought you really could reason with them, that you could hit some right buttons now and then, they would fairly add 2 plus 2 and then do, but they really won't. They have a huge resistance to it anyway, much bigger than I thought it was. A lack of character and integrity that is just much deeper than I thought. And that's disappointing, because I already had a pretty bad opinion of humans, and now it's a really bad opinion. You people suck at thinking. So anyway, till the next time and such. I haven't heard anything from, I did post a little comment on what's-his-face's Science Asylum, asking him how much he'd charge. To be critiqued, to have his science critiqued, but no response. 24 hours. Anyway, I'll keep trying. The other guy just hasn't got back to me yet. It still shouldn't be a problem. I mean, I asked him, blah, blah, blah. He says, oh, yeah, I got to do some more research, blah, blah, blah. So I said, okay, fine. No big deal. Take your time. Maybe I should have said, well, you're not going to take a month, are you? But we'll see.